the type of singular correspondence.
Thank you very much. So today I would like to explain a bit what we mean for Hodge-to-singular correspondence, and let me write a setup. So let's fix see a smooth projective curve over the complex number, and I will denote by M and D what's in the talk before has been called the moduli space of Higgs bundles. And I will take GLN Higgs bundle. And I will use the same notation, denoting E, a vector bundle of rank n and degree d on the curve C, and phi the Higgs field from E to E tensor the canonical class. Yes. And let me just remind you that by the BNR correspondence that says that this moduli space is the same thing as the moduli space of rank 1 torsion of sheaves, let's say, on the cotangent bundle of the curve, which are support on a curve in the linear system of n times the canonical section, and then whose Euler characteristic is something like d n minus 1 times the degree of kc over 2. That's not very important. I hope that the numerology is correct. The important thing is that this Euler characteristic depends on d. Okay, it's the same d here. So the goal of this talk today, we would like to explore the relation, how the cohomology of these spaces depends on the degree. You see, this variety, when you fix the rank, these are variety of the same dimension, but a priori there is no relation between those. There is no clear algebraic map, alteration, birational map between those. But still, I mean, there are some evidence that their cohomology should be related. And since I'm not imposing any condition of coprimality between n and d, this space in general will be singular. And since we want to study the symmetry of this object, it's better to change the cohomology theory, and instead of taking ordinary cohomology, take what is called the intersection cohomology. If you don't know it, just pretend that it's the ordinary cohomology. The idea is that for singular space, usually duality, like Poincare duality, are Lefschetz fails, but you can recover it if instead you work with this cohomology theory. Okay. So let me briefly mention, and maybe I will come back later at the end of the talk, what is the motivation? So what we would like to do in the future, if we understand what is the relation between all this cohomology when we vary the degree, then we could export what we know in the coprime case to the other degree. So the idea is to export symmetries of the cohomology of n and d, known in the coprime case, to arbitrary degree. And in particular, especially degree 0, because it's probably the space where everything started, because this is the case when m and 0 is really the space that is homomorphic to the space of representation of the fundamental group of the curve. So all the other space have an interpretation in terms of representation, but they are decorated. This is really the honest original one. And when I say symmetry here, I don't want to enter in detail, but what I'm thinking is maybe P equal W or topological mirror symmetry. So here I'm really working with the coarse moduli space and not with the stack. Okay, that's important. So how can we actually compare these spaces if we don't have a geometric map between those? Well, the strategy is the following. We have these two spaces, and both of them fiber on the base of the Hitchin fibration. Sending the Higgs bundle to the characteristic polynomial of the Higgs field. This is the Hitchin fibration. Now, what we can do at this stage, remember, we are interested in computing the cohomology or the intersection cohomology of this space. Now, as ordinary cohomology, intersection cohomology is the cohomology of some constructible sheaf, actually a constructible complex, which is called intersection complex, that I will denote in this way. But now, by the formalism of sheaves, this cohomology is the same as the cohomology on AN of the push forward of IC. So we don't really have a complete grasp on this, and we cook up a priori an even more complicated complex of constructible sheaf. Yes, but here we have an advantage that these actually splits in smaller term, thanks to the decomposition theorem. Decomposition theorem that is telling us that the cohomology that these sheaves, this complex of sheaves decompose in some summand supported on some subvariety of Z, and these are summand of these complexes supported on Z that we will call ghost strings. So if we want to understand how this cohomology depends on D, we better understand Z and understand this summand. So now our goal.
Sorry, what's that letter?
Is a curly S.
Okay.
For string. We want to determine or summand of the decomposition theorem. So Z and Z. Okay. So this is actually what the Hodge-to-singular correspondence achieved, and we will see that this summand, so the Hodge-to-singular correspondence is a way to express these Hodge-theoretic objects. I'm thinking of these strings in terms of the singularity of a fixed object Mn0. And notice that here I'm changing degree. That's quite a strange. Or in terms of the combinatorics of lattice polytope associated to compactify Jacobian. I will explain later.
Sorry, what is L in the goal?
This one?
No. Determine what in your goal? So you determine what is that like?
Determine Z.
I'm sorry.
Yes, the support and summand associated to compactify Jacobian. So let me recall first some previous work in this direction. Oh, other words. So I introduced the notation AN for the base of the Hitchin fibration, but inside these I can take some open sets, AN red and AN L, the reduced and the elliptic locus. This is the locus where the characteristic polynomial equal to 0. I mean, this is a polynomial. If I put equal to 0, I get a curve inside the total space of the cotangent bundle of the curve. And as the name suggests, I require that this is reduced. And elliptic locus in this context is the same, but I require that this is integral. Okay. So it follows from the work of Ngo that if I take that sheaf that I mentioned before, and I restrict it to the elliptic locus, then this has full support. What does it mean? It means that the only Z that appear is the wall base. So this, it has no proper summand. This has important geometric consequences. What this means in practice? It means that this complex it depends. It is determined by the restriction, by its restriction to any open set. Okay, let me mention that these summand here are done in a way that once you determine that generically, there is a canonical way how to extend them. Okay, so if you know that this object has no proper summand, this means that there is only one summand, and this summand is determined just generically on an open set, and there is a canonical way to extend it. So this complex, since it has full support, is determined by its restriction on any open set. In particular, the open set where the fibration is smooth. Where chi and d is smooth. But generically, chi and d is a torsor with respect to the same groups, abelian group scheme. And it's a property of abelian group scheme that the cohomology of their torsor is all the same. So this in particular means that this sheaf is independent of D. So the upshot here, to keep in mind, that all the times that you find some full support property, you should think that somewhere you are getting some degree or some independence from discrete data. Okay. But it's kind of important that here we restrict to the elliptic locus. Essentially, this is the locus where you avoid the support, the other support of the decomposition theorem. In the complement, you find this support.
That's a question.
Yes.
So if you have a torso, then there could be some monodromy as you move around. You're saying the monodromy would only be like a translation in that.
Exactly. So cohomologically,
as far as the cohomology is concerned, you don't see that. Is that
exactly. And then you are using also the degeneration at the page 2 of the Leray spectral sequence. Because what you are telling me is just something about the Ri of the push forward, and then you want to use the wall complex. Yeah. What I'm saying is that if you take other group scheme in C star group scheme, S1 group scheme, like S3 over S2, or S2 times S1 over S2, these are two torsor over S1, but they don't have the same cohomology. What here doesn't work is that you don't have the degeneration at the page 2 of the Leray spectral sequence. So let me make, this is important, that is an abelian. Oops. So a result that goes in the same direction, the result that the coprime case follows from the work of Lomont and Chaudouard. And in general, by Mauri and Shen. If L is a line bundle on C of degree strictly greater than 2G minus 2, and Mauri and Shen called this condition the Fano condition. Because if you take a curve inside a Del Pezzo surface, its normal bundle will have this property. While if I remember at the beginning, I said that we are parametrizing sheaf on the cotangent bundle of the curve. This is the Calabi-Yau condition. Okay, but if you are in the Fano condition, you have a bit of positivity that you can use to prove the following statement. If you take the moduli space of twisted X bundle, so now vector bundle with X field from E to E tensor L, then here they can prove unconditionally on the wall base of the Hitchin fibration that this sheaf has full support. Which means that if I take, but by this principle that I wrote here, is that the intersection cohomology of this basis is independent of D. Yeah, the Calabi-Yau case is more subtle. So maybe let me just mention, this has full support. How they prove this result. They say, okay, suppose that there is a support of the decomposition theorem. Then they use some formula from Lomone and Chaudouard that control the codimension of this support. But using that Fano condition, which translates in the fact that the dimension of the fiber of the Hitchin fibration is smaller than the dimension of the base, they can rule out the presence of this. If I take the same formulas in the Calabi-Yau case, I get a trivial equality, 0 equal to 0. It's not useful in any way. So the Calabi-Yau case is more subtle. And let me mention maybe a result by De Cataldo, Eilot, and Migliorini. In the smooth case, if n and d are coprime, so when m and d are smooth, they prove that they determine the summand of archi and d star IC on the reduced locus. And what I want to do today is to remove this assumption, but change the proof, because this proof really relies on the smoothness. They use the Catani-Kaplan-Schmidt to compute, to have a grasp on this object, but we don't have anymore this tool here. And our result again will be, there is this technical assumption also in ours, we restrict on the locus of reduced curve. It's open what happens outside, but it would be very interesting to understand what happens there. So as I said, here the smoothness is kind of important, but in our work, the singularity plays a crucial role. So now I will make a small digression about the singularity of this space. And since we will work always on the reduced locus, I will talk also of singularity over the reduced locus. So, singularities. Of M red and D. So what is a singular point of M and D red? I mean, this part could be generalized to the whole Dolbeault moduli space, but maybe the labeling will be a bit more complicated. So is a polystable object which is sum of stable objects, stable Higgs bundles, well, if we want a singular point, R is better to be greater than 1. And is polystable in the sense that the degree of EI over the rank of EI is equal to the degree of the whole Higgs bundle over its rank, which is D over N. So in particular, if I extract the partition of N given by the rank of the EI, this is a partition N of Ni. I mean, this rank needs to sum to N, but not any random partition, such that D over N times N prime is an integer. Because what is this number? It's precisely the degree of EI. Okay? And vice versa. All the times that you give me a partition of this type, I can cook up a singular point with that particular partition associated. So I call this partition, call such partition the integral. And we can formulate a geometric statement saying that our moduli space M, red, and D admits a Whitney stratification by partition type of the following form: N, red, and D is covered by locally closed set depending on the degree and labeled by partition which are the integral. And what is this locally closed set? This is the set of all Higgs bundle EPI with the property that the partition of the rank of the stable factor is the prescribed one. Okay. And let me introduce the last piece of notation. I call Wn an analytic normal slice to Mn0D. What does it mean? I have my moduli space Mnd, and inside here I have a stratum of the Whitney stratification. In the normal direction, I can take a slice and I call it Wn. And what I'm giving for granted here is that this slice is independent of the degree. I dropped the notation. And also that it doesn't depend on the point. That's something unusual in general for algebraic variety. Usually the analytic type of the slice depend on the point that you pick out. Whitney stratification means that the topological type of the slice doesn't change, but the analytic a priori may change, but not for this hyperkähler singular variety. That's a result of Cavietti. Let's put its name.
Why do you write a 0 on top of the M?
To say that this is the locally closed set. When I will drop it, I mean its closure. Otherwise, I could not take the disjoint union. Okay. So said, I'm ready to state the Hodge-to-singular correspondence, which boils down to describing the decomposition theorem for GLN Higgs bundle in arbitrary degree. So the first things to do is to prescribe. I need to say how a sheet decomposes in summand. I want to know where this summand is supported. So the first statement is concern the support of the decomposition theorem. So for any partition n of n, I introduce this subvariety of an red, which is the closure of the locus of characteristic polynomial whose irreducible factor at degree ni. So the characteristic polynomial is a polynomial of degree n. I take its decomposition in irreducible, and I extract the degree of these factors. This degree form a partition of n, and I'm saying that is the partition prescribed. And now I have the following dichotomy, the first part of the Hodge-to-singular correspondence, that says that, well, okay, if R is greater than 1, where R is the length of the partition, then Sn has the following behavior. Either it is the image of the closure of one of the strata before, but we say that this appears only if the partition is the integral. So if n is the integral. Otherwise, it is a support of archive and d star IC M and D, and this happens all the times if n is not the integral. So let me explain what's going on. We have two extreme cases. The degree 0 case on one side, and the coprime case, and everything in the middle, everything else in the middle, no? So when d is equal to 0, this equation can be always solved. This means that this is the most singular space, the space with the maximal number of singular strata. For r greater than 1, in the coprime case, that equation does not have any solution. And this is compatible with the sense, which means that our witness stratification has a single stratum. It means that this space is smooth. But what the theorem above is telling is that this is the case where we have the maximal number of strata of summand or support of the decomposition theorem of, well, the sheaf archive and d star IC. And here we have full support. Now on AN red, so a larger locus than the elliptic locus. So, and here we have an intermediate behavior. So this is a kind of conservation law that when you move from the left side to the right side, you lose some singular strata, but you gain some summand of the decomposition theorem. So you intertwine the singularity with the Hodge theory. That's why we call it Hodge-to-singular.
In the first case where the partition is the integral of the theorem, you're saying that Sn is not a support in that case?
Exactly, yes. Yes. Yeah, this gives the support of the decomposition theorem appears only on the Sn where n is not the integral.
Is the fact that it's not a support implied by that, or is that just related?
No. I mean, I want to say that there is this dichotomy. Either, I mean, it is in the theorem.
Sure.
Either you are in this case or you are in this case. And yeah, I mean, here plus, okay, not being a support, not being a support. But we can be more precise and also say what is the summand on that support. And this is the second part of the Hodge-to-singular correspondence.
Also, is there some relation to the number of irreducible components of the fibers?
Yes, yes. Hopefully I will come to that. Actually, this relies on the work of Go. Yeah, so maybe the more general version of the Hodge-to-singular correspondence is an effective version of the decomposition theorem. Maybe if you're not familiar with the decomposition theorem, let me just say that this is a very general fact that all the times that you have a proper morphism of algebraic variety, and maybe I should drop even algebraic variety, color should be fine. You have this decomposition, but this is an existence result for this decomposition. It doesn't give you the shape of the summand. For the Hitchin vibration, what we are aiming here is really give a complete description of the local system that actually appear. And it says the following. Let's denote Gn. This is the Jacobian. This is the group scheme that Andrew was mentioning in the first lecture, Jacobian of the normalization of the spectral curve, the relative spectral curve over an open set Sn0 in Sn. Then we can write that R chi and D star IC M and D is equal to the sum over all the integral partition of IC of the intersection complex of Sn twisted by some coefficient, which is this contribution that comes from the cohomology of this group scheme times a local system. And okay, there is a shift in dimension. So now modulus, maybe describing what is the index set. This is the statement of Ngo decomposition theorem after his proof of the freeness conjecture. So this actually comes from Ngo's paper, proof of the fundamental lemma. What is new is the fact that we know what are the summand of the decomposition theorem, and among these coefficients, this is kind of known, classical. What is mysterious is what this local system should be. And we determine it so where L and D is a local system on Sn0. And we have the following description of what is. Either it is the topology of a symplectic resolution of Wn, where Wn is a symplectic resolution of Wn, or is the topology of a poset where the poset, I owe you some explanation. I will come back. Let me just finish here. This is the poset of support, of proper support Sm, strictly bigger than Sn, support for R chi n d star of IC of M and D. So let me explain what I mean with this. With a picture. Let's consider, for instance, these two moduli space. We said that they fiber over the Hitchin fibration. And let's say that here we have a summand, a support of the decomposition theorem for these morphisms. So on top of this, there should be a local system, Ln1. But now I'm saying that these local systems come from here, from the singularity of this space. In which way? For each partition here, I have a singular stratum here, Mn0. And here I have some singularity in the normal direction. I take a symplectic resolution of these. Let me call this Wn tilde. And actually, I said that the local slice here is independent of the point that I pick. So this symplectic resolution is always the same. So its topology gives rise to a local system here. And what we prove is that this local system descends and gives rise to this one. So an Hodge theoretic object that gives rise, that comes from singularity. And now to be completely precise, one may wonder if this symplectic resolution actually exists. Although moduli space usually don't have symplectic resolution, but locally, this was already remarked by Kaliedin and Sorgel, locally symplectic resolution may exist. And it happens that over the regular locus, you always have this symplectic resolution, but it may happen that you have a lot of symplectic resolution. But luckily, they are all diffeomorphic. So the top cohomology is well defined. This interpretation holds if N and D are coprime. In general, we have this description. And here what I mean, so if I have a stratum of the decomposition theorem, I can take all the other stratum of the decomposition theorem, the proper one that contains this one. And by inclusion, they form a poset. Now I can take the CW complex, the realization of this poset, the CW complex obtained in the following way. All the cells of the CW complex correspond to the chain in this poset. We prove that this is shellable, which means that this poset has the homotopy type of a wedge of sphere. The number of sphere is this topology. And now here I'm saying that this is a local system, but these are only vector spaces. What I mean is that these actually are a representation of the fundamental group of this open set. And so in particular, a representation of these as representation is a local system on this open set. And where this comes from, the fact is that we know explicitly this is actually the automorphism group of the dual graph of the general spectral curve and actually is the automorphism of the partition. Now this singularity is a Nakajima-Quiver variety that is constructed out of this graph. So if you have an automorphism, these induce an automorphism of the Nakajima-Quiver variety, and so an automorphism on a representation on the cohomology. And here, I mean, this is a poset labeled by partitions. And so if I have the automorphism of the partition, it acts naturally on this poset. And okay, if I want to be very precise, actually here I should tensor by the sign representation, essentially by some Alexander duality here. Okay, so this is the complete statement. We have the full description of the decomposition theorem. And what I would like to do is to give you a sketch of the proof, because the proof is completely geometric.
Is your theorem over the reduced?
Yes, yes, we are all, yeah, sorry, you're right. That's a very good point. AN, right. Yes. So I already erased. Yeah, we asked for conjecture, this full support conjecture for equation is R chi n0 I C m n0 as full support on the wall basis. If this question has a positive answer, then I can drop this. For all degree, actually, not just for degree 0. So if I can prove this result, then one can prove that actually there are no summand of the decomposition theorems supported on the non-reduced locus. But let me give an idea of the proof. The starting point is a description of the VNR correspondence given by De Cataldo, Eilot, and Migliorini that hasn't been used that much in the literature, but I think it's very, at least as far as I know. Instead of working on the reduced locus, I can work on an even smaller locus of the Hitchin fibration. That is the locus where the characteristic polynomial is nodal. So in particular, this is a stable curve. So I have a classified map towards mg bar, where G prime is the genus of the spectral curve. On top of this space, I have a universal compactified Jacobian parametrizing rank 1 torsion-free sheaves on the universal curve. And I gave two definitions of the Hitchin of the Dolbeault moduli space, either in terms of Higgs bundle or sheaves on the cotangent bundle of the curve, in particular rank 1 torsion-free sheaves on the spectral curve. So actually, I had a good formation of the moduli space. There is a fiber product like that. So the idea is now to translate our problem of understanding the intersection complex here in a problem of the universal compactified Jacobian. Okay, so essentially what we are doing is, if this is the Dolbeau moduli space, we are enlarging the base of the Hitchin fibration to a versal deformation and enlarge these to this universal compactified Jacobian. Why? Because we want to use the formulas of Lomon and Chaudouard that I told you works when, essentially when the dimension of the fiber is smaller than the dimension of the base. In this way, with this enlargement, we haven't touched the dimension of the fiber. The fiber are still compactified Jacobian. The dimension doesn't change, but the versal deformation is much bigger. Okay. Okay, so this is, I think, a key input to keep in mind, but let me explain how we want to proceed. So we want to compare these two spaces. And in general, one can show already in degree 2 that if I take the push forward of the IC, this in general will be different. And a posteriori, we will show that this equality holds only if the GCD of N and D are the same. But in general, they will be different. So the idea is that maybe we should change the sheaf here in such a way that we gain this equality. So when we push forward, we get inequality. A sheaf that should be related to the intersection complex, otherwise. So the idea by myself and Luca Migliorini is that the push forward via the Hitchin fibration of which sheaf? A sheaf that admits M and D as a direct summand plus some correction that I will write now is independent of D. So that maybe those two are not equal, but we can measure the difference. And what is this sheaf? Actually, it's a semi-simple perverse sheaf. Sum of IC sheaf. Each of them are supported on the strata of the Whitney stratification, and they are twisted by a local system, which is a local system that in the theorem appear here when D is equal to 1. Okay. This seems complicated. Oh, well, summing over all partition and the integral. This seems complicated, but you will see that we'll give another geometric description of this that is very clear. Well, I can mention it immediately because keeping in mind this BNR correspondence, what we proved. Yeah, sorry, I spoiled my own result because I already said that we proved that actually it was a result of Migliorini, Scende, and Viviani in the smooth case, and then in the singular case, we prove it, Luca and I, that if I call this map pi, the push forward of the IC of JD has full support. And the idea, as I mentioned before, is use Lomon and Chaudhary inequality, because now we are in the setting where we could apply sort of Fano condition. It's not really meromorphic Higgs bundle, but sort of that kind of idea. And I mean, once we have this, by what I mentioned at the beginning, this is independent of D. And so what is this mysterious shift here? This is nothing else but the intersection cohomology of the compactified Jacobian, universal compactified Jacobian, restricted to M and D. Why? Because I used just a proper base change to say that, okay, this object is independent of D. If I restrict it to the base of the Hitchin fibration, the classifying map here doesn't depend on the degree. So this will be, again, independent of D. But now by base change, this is the same as R chi and D star of IC of JD of AN star of M and D. Okay? Maybe.
You explain what is restriction of the atom board? Because they don't live on the same space. I mean, IC, J bar D.
And I, what one?
No, the other one is, what is restriction? Ah, okay.
And then you take intermediate extension.
The pullback.
Yes, the pullback.
Pullback and major extension.
Yes, it's roughly a restriction in the sense that there is an isotrivial direction. Yeah, I'm cheating here, you should take a slice. There is an isotrivial direction here, but the cohomology of this space doesn't change in that direction because the isotrivial direction is the C star term or the part of trace that is just a shift of the spectral curve. But the cohomology of the fiber doesn't change. So I can pretend that really these embed inside here and these also embed inside. Yes, but you're right. I mean, now, at the beginning, I said you can pretend that intersection cohomology is the same as cohomology, so this should be the constant sheaf. But you know, for the constant sheaf, it's true that the restriction of the constant sheaf is the constant sheaf of the restriction. For the intersection complex, this is not the case. The intersection complex is remembering something about the singularity. And so when you restrict it to a locus, you lose the information of the singularity in the normal direction. So these two sheaves are different. But now understanding this sheaf becomes just a problem of understanding the singularity. So you see, again, we start with Hodge theoretic problem, but we end up to study some singularity. And this formula here should be reminiscent for the people used to the decomposition theorem, for semi-small maps. And the fact is that hidden here, there is the theory of hypertoric quiver variety, which admits small resolution. So morally, at least cohomologically, we are saying that these two moduli space, at least cohomologically, look like a semi-small resolution of the other. It doesn't make sense geometrically because there is no map between those. But what we see here is what we would get if there is this semi-small map. Okay. And
3 more minutes.
3 more minutes. Let me just conclude with some applications. So once you have the explicit form of the decomposition theorem, one can prove that the intersection cohomology of M and D on the reduced locus is built out of the intersection cohomology of M and 0 Mn prime 0 for n prime smaller than n. Essentially because the push forward of all these objects will turn out to be independent of the degree. What depends on the degree is just this local system. But this local system accounts to choose a isotypic representation inside some space like this of an action of a symmetric group. It's kind of involved the relation, but I think it's a nice result on its own because you know, since the 80s we wanted to study this object and we turn out to study the coprime case, and here we are saying that at least cohomologically the degree 0 case is the building block for the other. Maybe let me mention some other result. Stabilization. We prove, but this follows immediately from the first result about the support, that if I take the limit for n which goes to infinity of m and d, and I take, so this actually is an Hodge structure, so I fix some PQ part, this limit exists and is independent of D. So I said that this cohomology actually depends on D, but asymptotically it doesn't. And let me mention the relation, I mentioned at the beginning some relation with symmetry of these spaces. So the PI equal WI conjecture. So one of the output of our result is that there exists a surjective map from the cohomology, let's say for the degree 0 case, so that I can remove the red. You see here, I always put the red. Here is one. So we have a map between these two spaces, the cohomology of the smooth space and the cohomology of the singular space. And since we work on the base of the Hitchin vibration, this map, that is just the induced map in cohomology, preserve the perverse filtration. So equal W is a conjecture about two filtration on these spaces of very different origin, but surprisingly, the conjecture says that the two should coincide. And now we recently, actually in degree 2, we have the proof of Hausel, Migliorini, and the Cataldo, but let's say in general, in the coprime case, we now have the proof of P equal W's on this side. If this map actually preserve also the weight filtration that we don't know at the moment, then you would get the perverse, the P equal W in degree 0 and for the same argument in any degree. So the idea is that in order to prove this conjecture like P equal W topological mirror symmetry, one should prove it in 1 degree and then using the information about the decomposition theorem, propagate the result to all the other degrees. Okay, thank you very much.
We have time for question or two.
So since you don't seem to be scared of singularities, can you say something about maybe modulus of Higgs bundles for other groups, maybe classical groups?
We are working on this. It's very complicated because the basic, so here what I didn't even mention is that the Hitchin vibration is, let me say, in Go vibration, weak abelian, delta regular. All these attributes are not clear on the wall base of the Hitchin vibration in for arbitrary group. So we are first working on those, and then hopefully we will come to that. Also studying the singularity of these spaces, kind of tricky. Lovely.
Some progress.
Yes, yes.
Just for curiosity,
yes.
Integer homology have ring structures.
Hey, that's the problem, is that intersection cohomology doesn't have it.
Yeah, but in this case, does it have it?
In this particular case, you can build up a ring structure, maybe in low genus 2. We were working with Tamas.
Don't is ideal.
No.
No.
That's the point. That's the tricky point. You can cook up a ring structure with preserve the perverse filtration, but this is not an ideal. So that's the problem, no? One other idea would be, okay, we have the proof for P equal W, try to adapt it for the singular case, but that's not obvious because all the proof that we have of P equal W use the cup product. And here we don't have a priori a ring structure.
Sorry. Okay. But for arbitrary G, you don't have a version for the degree that gives you something smooth, right? Like what's your version of the?
Yes, so we were working also on that. I mean, we have different ideas, but maybe you could take an extension with GM, like for GLN and SLN, and use these as notion of degree. But maybe finding more canonical things would be interesting.
So this stabilization lemma, one of the fixed memory in the arm, as n increases, the codimension of the singular locus
Exactly.
increases as well. So
exactly, that's the point. If you fix, I mean, this is an easy consequence. If you fix P and Q,
you get absorbed into the
exactly, you get absorbed in the smooth case. Yeah. That's why I said that's an easy consequence of that. That's
Okay, thanks again.